All right, we're going to continue. Where did we leave off last time?
Actually, I do have a question. I was absent for lab yesterday, and I heard you mentioning that we were coming early.
You can come to the morning lab.
What time is that?
9:30.
9:30?
Yeah,
Oh. Thank you.
9:30 to 12. Where did we leave off last time? We finished phosphoric acid? Okay, I think we finished that. Okay, so acids are pretty much the same. For the acids, we're looking for all the hydronium ion producers, and we're going to go in order of descending Ks. We're starting with the biggest K, the smallest, and hopefully stepwise works. So today we're going to talk about bases. For bases, we have Kb. B stands for base hydrolysis. Actually, bases don't ionize. Bases just hydrolyze water. So an example of that would be something like sodium amide. Sodium amide is a strong base, right? This is a strong base, but when I look at sodium amide, first thing I think is it's a soluble salt. And so sodium amide, being a soluble salt, should dissolve in water. And so it forms aqueous sodium amide. But aqueous sodium amide is a strong electrolyte. Soluble salts are strong electrolytes. And so it's going to ionize. And so a lot of people will think this ionization step is because it's a strong base. No, this ionization step is because it's a soluble salt. The strong base is actually amide. And so does the strong base ionize like amide? What would it ionize into if it were to ionize? An H plus and an NH2 minus? Would that be it? No. The strong bases, or in fact, bases do not ionize. Bases do what? Hydrolyze. And so strong bases hydrolyze water. So bases will react with water to form what? Well, base is a proton acceptor, so it's going to form ammonia and hydroxide. And so this is the strong base. Strong bases hydrolyze water completely. Strong bases hydrolyze completely. In Chem 1B, this is what we say. This is what you learn in Chem 1A. In Chem 1B, you would do this. You would say that Kb for this is what? If it's very large. That's okay, so strong bases hydrolyze water completely. Weak bases partially hydrolyze water. And so their Ks are smaller. So let's take a look at a weak base here. So this was for a strong base. I forgot to write that down. Strong. Okay, let's look at a weak. A weak base would be like ammonia. Ammonia will partially hydrolyze. Ammonia does not ionize. A lot of people try to ionize it into ions, but no, it's going to react with water to form ammonium and hydroxide. And so Kb is the base hydrolysis of water to form hydroxide. Both of these are going to produce hydroxide in solution. And so we see Kb for this is quite small. Kb turns out to be 1.8 times 10 to the minus 5. It has the same number as acetic acid, but they aren't related. If we went out to 3 or 4 sig figs, they'd be different numbers. Both round to 1.8 times 10 to the minus 5 by coincidence. All right, so for base solutions, we generate hydroxide, and so we should talk about this. We should talk about pH, pOH, pKw, hydronium, and hydroxide concentrations. So let's look at these in more detail. So that we know that Kw is equal to 1.0 times 10 to the minus 14, which is equal to the hydronium ion concentration times the hydroxide ion concentration. And so from this, the hydronium ion concentration at equilibrium times the hydroxide ion concentration at equilibrium is equal to constant. And therefore, if the hydronium ion concentration goes up, the hydroxide ion concentration must go down, and vice versa. And so the hydronium and the hydroxide are tied together in a seesaw type relationship. One goes up, the other must go down, the other goes up, the other must go down. And so we see that here. Normally we're interested in pH. You know, pH is equal to negative log of the H plus or hydronium ion concentration. And the P here is the power function. The P is we just take the negative log of whatever we're interested in. And so this is the power of the H plus, and so that would be the negative log for the H plus concentration here. So we could do other power functions as well. And so one of the useful, very useful power functions is pKw. pKw would be the negative log of kW. The negative log of this, well, when we look at the power, it's 14, and then we change the sign because it's invert related. And so the pKw is equal to 14.00. We see here we have two sig figs here in the normal function. In the power function, these would be the two sig figs here. Two sig figs here. And so we get pKw. Well, pKw, well, this is going to equal the negative log of this whole thing over here. It's going to be the negative log of the hydronium ion concentration times the hydroxide ion concentration. So we can distribute that out, and so we end up with this, that the pKw is equal to the pH plus the pOH, which is equal to 14.00. And so for base solutions, what we're going to do is we're just going to calculate the pOH, the power of the hydroxide ion concentration, and then convert it into pH, since they're tied together. You know, if the pOH goes up, the pH goes down. If the pH goes up, the pOH goes down. And so these are going to add up to the constant 14.00. And so what is the pOH? The pOH is just the negative log of the hydroxide ion concentration. Okay. So let's take a look. When we do multiple equilibria, we usually are trying to do one or two things. The first thing is we just want to figure out what is the pH, you know, of this acid or the base solution, the pH. Normally for pH calculations, we just do step one only. Say step one only. Okay, unless A, step 2 has a K value about, has a fairly large K value. If step 2 has a fairly large K value, then that's going to contribute, you know, some hydronium or hydroxide or whatever to solution. And so what is a fairly large K value? Yeah, 10 to the negative 2. Like 10 to the negative 1, 10 to the negative 2, maybe 10 to the negative 3, but it's mainly 10 to the negative 2. That's what you're going to see most. And so if the step 2 has a K of 10 to the negative 2, then that's kind of big. We should worry about it. And so we should incorporate step 2. Or B, we're dealing with very dilute solutions. The example of a very dilute solution was like 1.0 times 10 to the minus 8 molar HCl. You know, when we look at K here, step 1 has a K very large. But step 2 would be KW. Step 2 has a KW, which is 10 to the minus 14, which is very small. And so even though step 2 is very small, we still have to worry about it. The reason we have to worry about it is because 10 to the minus 8 molar HCl is almost like pure water. It's very close to pure water. And so if you're very close to pure water, then what's the most important equilibrium? It's probably going to be the KW, right? If it's pure water, it's KW. And so in other words, we have to worry about it if step 1 doesn't yield much hydronium. So for example, like this. You know, in Chem 4, you never worry about KW because we generate so much hydronium or hydroxide in step 1 that KW doesn't really contribute much. But if step 1 generates minimal hydronium, like 10 to the minus 7, 10 to the minus 8, 10 to the minus 9, maybe 10 to the minus 6, etc., molar hydronium, then we better start worrying about water. Because do you know how much hydronium water can generate? KW will generate at the max 10 to the minus 7 molar. And so we think, will 10 to the minus 7 molar have an impact on it? Well, if you're generating 10 to the minus 6 molar hydronium in step 1, then we have the potential to generate up to 10 to the minus 7 molar in step 2, then we got to worry about it, right? Because that would be a contribution. For sure, if we're at 10 to the minus 7 molar hydronium in step 1, then for sure we got to worry about water. Our example is 10 to the minus 8. We generated 10 to the minus 8 molar hydronium in step 1 here. If you're generating 10 to the minus 8 molar hydronium in step 1, then water is going to be a significant contributor. Do we see that? It's because of the common ion effect. So the max is, in reality, it's going to be less. You know, it's going to be less because of the common ion effect. So in reality, it's more like 10 to the minus 8 we're going to generate. But if we have 10 to the minus 6 to begin with, and we generate 10 to the minus 8, then it's still significant. You know, 1 part per 100, you know, or 1%. And so it's max in pure water, but if we have some hydronium present, we got the common ion effect. The common ion effect keeps that lower. Does that make sense there? And so that's what we do for multiple equilibrium. For inventories, you know, we have to do all steps required. And so we're always looking for things to save ourselves a little bit of time. So all steps required for inventories. So let's do some more calculations, but this time with bases instead. One of the things, let's go back to bases. One of the things is we're going to need KBs for bases. But, you know, when I look for KB chart, it's very small. In fact, if you look at that acid-base chart there, do you see any KBs listed there? There are no KBs. And so a lot of KBs are missing. Many KBs are missing from the chart. And the reason is we don't need them. It turns out there's a relationship between Ka and Kb for conjugate pairs. These can be calculated. The calculation is that Kw is equal to Ka times Kb if A and B are conjugates of each other. Therefore, if I want the Kb for ammonia, and I don't see that on the chart, then the Kb for ammonia is just equal to Kw divided by the Ka for its conjugate. What is the conjugate? Ammonia is a base, so its conjugate acid would be ammonium. And so, there. We could see that in the book they proved this. You just write out the expression for Ka, you write out the expression for Kb, everything cancels except for hydronium and hydroxide, which is Kw.
So what is an amphoteric species?
If you have an amphoteric, it's the same thing. You know, let's do an amphoteric species. And so an example would be something like sodium dihydrogen phosphate. Dihydrogen phosphate is amphoteric. Amphoteric means it's going to have a Ka and a Kb. The Ka for dihydrogen phosphate is given. The Ka is 7.1 times 10 to the minus 8. Or no, that's wrong. 6.3. 6.3 times 10 to the minus 8. That's given off the table. But the Kb is not. And so if we were to figure out the Kb is going to equal Kw divided by the Ka for the conjugate acid. What is the conjugate acid of H2PO4 minus? Well, the conjugate acid is phosphoric acid. And so this is 1.0 times 10 to the minus 14 divided by the Ka for phosphoric acid, which we saw yesterday, or day before, 7.1 times 10 to the minus 3. Well, the chart is different than our book. So we'll try to go with the books. Our book is more up to date. Let's bring that. What do we get here? One point four oh eight. So we'll just carry one extra digit. 1.40 times 10 to the minus 12. All right, sodium dihydrogen phosphate is an example of an amphoteric species. It can go either way, right? And so we're going to encounter three types of solutions in this chapter. Acid solutions. For acid solutions, we look for all the hydronium ion producers. For base solutions, we look for all the hydroxide producers. For amphoteric, we have to look for both. Because what happens with an amphoteric species, I'm jumping ahead because I was going to talk about this a little bit later today, is it can collide with water in two ways. One, it can collide with water and accept a proton. The other, it can collide with water and donate a proton. And both collisions happen. Which one's more favorable? Donating a proton or accepting a proton for H2PO4 minus? Donating a proton because Ka is bigger than Kb. And so the reaction where these two collide and then this donates a proton is more favorable. H3O plus HPO42 minus. This is more favorable because Ka is 6.3 times 10 to the minus 8. Then if it collides with water, if it collides with water and accepts a proton, it's slightly less favorable. And so if it accepts a proton, we're going to form H3PO4 and hydroxide. This is our Kb, which is 1.40 times 10 to the minus 12. And so it looks like we're going to form more hydronium than hydroxide in this solution. And so what we have to do in this is we do both. We do both reactions, right? Figure out what we get. And so let me talk about this more in a little bit because this is more complicated than an acid solution or base solution. Let's just stick with a base solution for right now. And so we'll come back to this. So let's take a look at ammonia first, and then figure out the pH and the inventory for aqueous ammonia. Go here. Let's say I have 0.100 molar ammonia. I want to figure out what is the pH, what is the inventory of this solution. So if I got 0.100 molar ammonia, ammonia is a base. And so it's just ammonium and water. Ammonium and water will form ammonium and hydroxide. This is base hydrolysis, or Kb. Kb is always base plus water, Ka is always acid plus water. It's hydrolysis. And so I'll just assume nothing's happened, so this is going to be 0.100 molar. 0 and 0, so no molecules have collided yet. Water, we leave out. And so then we'll allow collisions to happen, so some ammonia will collide with water to generate some ammonium ions and some hydroxide ions. And so to equilibrium, I'm going to expect some of the ammonia to be lost to hydrolysis. But since a weak base, I don't expect a huge amount to be lost, right? Just partial. So this is X molar, this is X molar. And so for bases, the calculation looks very similar. You know, this is going to be ammonium, the products, ammonium and hydroxide divided by the reactant. This gets ammonia. So this is going to give me X squared over 0.100 minus X. Then I don't bother thinking about it, just do the simplifying assumption. So this gives me X squared over 0.100, and therefore X is equal to what? So, well, this is equal to 1.8 times 10 to the minus 5, which we could look up. So this is going to be the square root of 1.8 times 10 to the minus 4. Okay, 0.0134. Okay, maybe I made a mistake. This is 10 to the minus 1, 10 to the positive 1, 10 to the minus 4.
Minus 6.
Is it minus 6? Yeah, 1.8 times 10 to the minus 5 times 0.1. You're right, it's 10 to the minus 6. Be 10 to the minus 5 times 10 to the minus 1. Sorry. This is too big, that's why.
So just add a zero.
Yeah. Is it 1 0 or more?
It's 2 zeros and 1 3.
Okay. So 0.00? Okay, that sounds about right. 0.00134. And so this is going to be 0.100 minus 0.00134. So this would be 6, 6, 8, 9, 0, 0. In other words, we have 1.34% reaction, or 1.34% hydrolysis, or 1.34% ionization, although bases don't ionize, right? But sometimes they'll just call it the base ionization constant.
What's the power of KB?
10 to the minus 5. So here's a KB table. A lot of species are missing, but ammonia is there. 1.8 times 10 to the minus 5. There are a lot of other, what do you call these? A lot of other what? There's ammonia and a lot of other bases, but what kind of bases are those? Carbon-based bases? A lot of other, when I look at these, I see a lot of, look at the names: aniline, codeine, diethylamine, dimethylamine, ethylamine, hydrazine. A lot of other nitrogen-based bases, yeah. A lot of other organic bases, yeah. A lot of other, what's that? Amines with one N. Right? I see a lot of amines. Everything else is missing. But anyway, let's go on. So it's about 1.34. We got to double check this. So it's 0.00134 here, molar. 0.00134 molar here. Okay. So let's just double check our K to make sure it gives us 1.8 times 10 to the minus 5.
What,
1.82 times 10 to the, okay, negative 5?
Yeah.
That sounds good. That looks good. And so this looks good. Now, if we're interested in pH, we would stop here. Because what I would do is I'd look at the hydroxide. The most hydroxide I'm going to get from Kw would be about to the negative. The most hydroxide I'll get from Kw is going to be 10 to the minus 7. In fact, I'm never going to get 10 to the minus 7 because 10 to the minus 7 is if there's no, if there's no predator around. And so it's going to be less. And so here, in this case, even if I get 10 to the minus 7, will that have an impact here? A significant impact? No, because that's going to be too many digits out. It's going to be out here. We're going to round that off anyway. And so but in reality, it's going to be more like a 10 to the minus 8, 10 to the minus 9 contribution. And so if I were interested in pH, I wouldn't even bother with Kw because I already see right off it's not going to contribute any hydroxide to this. Do you guys see that? And so I would stop here and I'd calculate my POH and then figure out what my pH is. And so what is the POH?
It's 2.87.
2.87, which gives us a pH of 11.12. So we get a pH of 11.12 and done with this problem. But if I want the inventory, I'm going to have to go to the next step. And what would the next step be? Oh, are there any other hydroxide producers here? Yeah, there is. Water. Yeah. And so I'm going to go on to step 2. H2O liquid plus H2O liquid. This is going to produce hydronium plus hydroxide. And then what I'm going to do is I'm going to carry down this hydroxide to step 2 here. And so this will pretty much be the end of the road for these two. Yeah. So I'll bring this down to step 2, our waters, ignore those. And so we'll assume nothing's happened, so there's no hydronium, but there's going to be hydroxide present from step 1, 0.00134 molar here. And so this is going to be plus X molar, plus X molar. And so we'll get X molar and 0.00134 plus X molar. And so here's what I mean by 10 to the minus 7. If it were 0 and 0, we get 10 to the minus 7 molar. But since we already have a bunch of hydroxide present here, we're going to get a lot less than 10 to the minus 7 molar, so that it equals the constant Kw. And so Kw is going to equal 1.0 times 10 to the minus 14, which is the hydronium times the hydroxide. So here we're going to use the simplifying assumption. We get X times 0.00134, and therefore X is, somebody calculate our X value? Do you see how little we contributed? This is because of the common ion effect. If there was 0 common ion, we would have gotten 10 to the minus 7 molar. But since we had so much common ion there to start with, we barely formed any, 10 to the minus 12. Adding this additional 10 to the minus 12, is that going to change the POH? So we have 0.0134, now we got 11 zeros, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 zeros and a 746. Is that going to change our POH? Not at all. I mean, this is going to come out 0.0134. That's a good thing, because if this changed significantly, what would have happened to step 1? It would have perturbed it. And if it perturbed step 1, we would have to solve this simultaneously, right? So, but hydronium was significant. Hydronium came out to 7.46 times 10 to the minus 12 molar. And so this would be the final for the hydronium, hydroxide, ammonium, and ammonia. And then we're set. Okay, that would be. Okay, let's do the next one here. The next example we'll look at is 0.100 molar sodium amide. And so we know that amide's the strong base here. Amide will attack water to form ammonia and hydroxide here. And so initial, we'll set up the ice table, 0.100 molar amide. We'll assume nothing's happened. Water, blank. Water's got to be there, otherwise we aren't going to have this reaction occur. But we ignore it because this activity doesn't change. All right, we know what Kb is. Kb for strong bases is very large. And so if it's very large, it's a one-way reaction. And this is going to go to completion. So this is going to be 0 molar, 0.100 molar, and 0.100 molar. For bases, we look for hydroxide ion contributors, because what we want to do is we want to figure out the total hydroxide present so we can get the POH of the base solution and convert it into pH, right? And so we just go in order, all right? So this would be step 1. Step 2, who else is going to contribute hydroxide? Water. Water will contribute hydroxide. But this is very tricky, this particular problem, because there's also another hydroxide contributor present, the ammonia. Which one do you think will contribute more hydroxide, ammonia or water? Ammonia. Ammonia is a much better base than water. And so in this particular instance, step 2 is not going to be Kw. Step 2 will be NH3, Kb for NH3, because NH3 will be the next biggest hydroxide contributor. And so what we do is we start off with the biggest K and then go down in order of descending K. And so here we're going to have ammonium plus water. This is going to give us ammonium plus hydroxide. The ammonia concentration, we drop this down to step 2 here. It's going to be 0.100 molar. We assume nothing's happened. And so there's going to be 0 ammonium. But the hydroxide is not 0. You know, the hydroxide is not 0 because we have hydroxide from step 1 going down to step 2. And so the hydroxide in step 2 will be 0.100. So which direction is the change going to be? Is it going to go right or left? We've got a lot of hydroxide there. It's got to go to the right. So this is going to be minus X. The reason it's got to go right is because we can't go below 0. So this is going to go positive. Positive here. And so in equilibrium, we're going to have 0.100 minus X molar, X molar, 0.100 plus X molar. Okay, so this should be the next biggest hydroxide contributor because Kb is 10 to the minus 5, whereas Kw is 10 to the minus 14. And so Kb for this is going to equal the ammonium concentration times the hydroxide ion concentration divided by the ammonia concentration. And this is 1.8 times 10 to the minus 5. So this will equal X times 0.100 plus X divided by 0.100 minus X. Okay, we just go ahead and try the simplifying assumption. See if it worked. Did it work for the last one? I didn't justify. Yeah, it worked. I mean, it was such a small change. 7.4 times 10 to the minus 12. This would be about 10 to the minus 3. So 10 to the minus 12 over 10 to the minus 3 would be 10 to the minus 9 times 10 squared would be 10 to the minus 7. This is a 10 to the minus 7% change, which is nothing. Over here, we'll try it, and so this is going to equal X. Therefore, X is equal to 1.8 times 10 to the minus 5. And so this is 10 to the minus 5 over 10 to the minus 1 is 10 to the minus 4 times 10 squared is 10 to the minus 2. So this is about a 10 to the minus 2% change. A 10 to the minus 2% change is way less than 5%. And so the simplifying assumption is no problem here. Okay, so we'll get the ammonia concentration. The ammonia concentration is going to be 0.100 minus 0. Now I need 4 zeros. 1, 2, 3, 4, and a 1, 8. So this is going to give me 10, 2, 8, 9, 9, 9, 0. 0.099982 molar. The ammonium concentration here is going to be 1.8 times 10 to the minus 5 molar. And the hydroxide ion concentration here is going to be 0.100 plus 0.123418. This is going to be 0.100 sub 0.18 molar. And so we'll double check this here. Can somebody double check the K calculation here and see what we get?
Explain what happened from step 1 to step 2.
From step 1 to step 2 is first we had to figure out what step 2 is. And so figuring out what step 2 is it Kw or Kb for ammonia? It turns out it's Kb for ammonia. It's Kb for ammonia because we expect more hydroxide from ammonia than water. Okay, and so all we do is we bring down everything from step 1 that we can bring down, we bring it down. And so step 1 generated ammonia, we have ammonia. Step 1 generated hydroxide, we have a hydroxide. Step 1 didn't generate ammonium, so ammonium is 0. That's how we got from step 1 to step 2. Does that answer your question or no?
Why do we get 0
0 molar for, is that NH2? Mine?
Oh, you mean how did I get from here to here?
Yeah.
Well, because I know KB is very large. What does it mean to have a very large KB? It means the reaction goes to completion. And so you consume all your limiting reagent. Water's in excess. Your limiting reagent is amide. It goes to 0. We generate what's a 1 to 1 mole ratio. This is stoichiometry, Chem 1A stoichiometry. Just done with an ice table. So it's just because KB is very large. Does it check out the K for, okay. Checks out. What did you get? Okay, times 10 to the minus 5. Good. That's good. Checks out. Okay, the thing we gotta always ask ourselves when we're doing stepwise is, did this step upset the previous step? Why or why not? Did this step perturb the previous step? Yes or no? So does step 2 upset step 1? Perturb it? Yes? Yes, because there was a change here, right? It seems like there's a change here. So it should have upset the previous step. Because when we recalculate K up here, it's not going to be the same, right? Or no. No, because this is going to round back to 0.100. That rounds to about 0.100, so it really didn't change that much. Or no, because we can't perturb step 1. Step 1 is a one-way reaction. No matter how much hydroxide changes or ammonia changes, it's not going to force it backwards. So we can increase these by a significant amount and nothing's going to happen because it only goes one way. Which one is it? The first, or the second, or the third would be the best answer. The third. The third is the best. You know, when we have a KB that's very large, so what if this grows a little bit bigger? It's still going to be smaller than this because very large, I don't know what that means, right? It's just very large. And so we don't perturb these. When Ks are very large, it's like this. Well, just leave it like that. So no matter how much these would have changed, I could have changed these by 50% or 100%. It won't impact this because this is a one-way reaction. Does that make sense? All right. All right, what's next? What's step 3? Water. Yeah, step 3 is going to be water. So the next biggest hydroxide ion contributor will be water. So let's go ahead and do that. Step 3. Water plus water produce hydronium and hydroxide. The initial hydronium, we're going to assume no water is hydrolyzed yet, it's 0. But the initial hydroxide we're going to carry from step 2 to step 3. And so here we're going to get 0.100 sub 018 molar hydroxide from the previous step. And so the only thing that can happen is we can go up from 0, so this is going to be plus X plus X. So this is a common ion. And so will water contribute a significant amount of hydroxide to this? What's the most hydroxide we're going to get from water? 10 to the negative 7. Will 10 to the negative 7 make any impact on that? No, absolutely none. So if we're interested in POH, we're already doing way too much work. But we're interested in inventory, so we have to do this. Because even though the hydroxide doesn't change, really, the hydronium does. What Petrucci does is he doesn't set this up as nice. He sets this up just as a KW calculation, usually. And so KW, this is going to equal the hydronium times the hydroxide, which is X, times, oops, I screwed this up, this is 0.100. 100 sub 018 plus X. 0.100 sub 018 plus X. This is going to equal 1.0 times 10 to the negative 14. We expect the SA to work pretty well here, so this is going to be X times 100 sub 018 is equal to that, and that means X is equal to what? Okay. 9.99 times 10 to the negative 14. That's barely any additional hydroxide, right? And so, well, that is significant in terms of hydronium, because now we have 9.99 times 10 to the negative 14 molar. And then over here we have 0.100 sub 018 plus point, and then we need 13 zeros. It's not even worth writing out. This is going to come out to 0.100 sub 018 molar. And so the final concentration of hydroxide is this, the final concentration of hydronium is this. This carries down, this doesn't, so that's the final concentration of ammonium, and this would be the final concentration of ammonia. So these are the species present at equilibrium. Right. Now, some confusion comes up. For example, wait a minute, ammonium is a acid. And so if I have ammonium will hydrolyze water to form hydronium. If I form more hydronium, that's going to cut down the amount of hydroxide I form. And so really this is not zero, is it? Should this be zero because I have ammonium present? The ammonium hydrolyzes water because I can't stop the collisions. Ammonium is going to collide with the water to form hydronium and ammonium. And so shouldn't I factor that in here, right? Because I have another hydronium ion producer. The other hydronium ion producer is right here. Right? And so what is the answer? Factor it in. Maybe I need to do a Ka calculation. Let's do this as an aside. Maybe I need to do a Ka calculation because I've got ammonium. In fact, I got 1.8 times 10 to the minus 5 molar ammonium. And that's going to hydrolyze water, H2O liquid, plus, or not plus, but to generate ammonia plus hydronium. So I assume nothing's happened, but you know, this would be a step 2B before I get to 3, because shouldn't I figure out how much hydronium I'm going to get from the ammonium and then plug that in here because, right? Yes? True or false? True, I should do 2B and then 3, or false? I don't need to do 2B. Well, I gave you a simple rule. The simple rule is this. In base solutions, we only look for hydroxide contributors. We don't care about hydronium contributors, but you say, well, aren't we going to screw up the calculation if we ignore the hydronium ion contributors? And the answer is we aren't ignoring the hydronium ion contributors. The reason we aren't ignoring them is because of this. If you look at what this equilibrium describes, this equilibrium describes the equilibrium between ammonium and ammonia in terms of pH. And so this is the ammonia equilibria based on the pH. If you look at this equilibrium describes the ammonia and ammonium equilibrium in terms of pOH. And so if we were to do this, we're doing the same thing over again. We're doing it twice. This is redundant. Redundant because pH and pOH are tied together like a seesaw. So if one goes up, the other goes down. And so the only difference is the number here. You know, if this came out as a pH of whatever, then the pOH would have come up at the other end of the seesaw, right? And so this is the same equilibrium. In fact, this is the same equilibrium as 2, except that except 2 is in terms of pOH. Does that make sense? Let's do another example to show it. So this would be redundant. We wouldn't do it. Let's go back to our phosphoric acid. When we do phosphoric acid is an acid, right? It's not a base, it's an acid. So acid is going to hydrolyze water to generate hydronium. So we're going to get H3O plus H2PO4 minus. Okay, this will be our step 1. But what should our step 2 be? Our step 2 is going to be H2PO4 minus, but H2PO4 minus is going to be either Ka or a Kb. Which one should we do? You know, because H2PO4 minus is amphoteric, so it can collide with water to form hydronium, Ka, or it can collide with water to form hydroxide, Kb. Which one should we do? Well, you either memorize the rule. The rule is for acid solutions, you only do Kas and Kw. For base solutions, you only do Kb. And so what we'd say is we would ignore Kb. But is it really justified to ignore Kb? Because what I did in my step 2 was I did this, H2PO4 minus plus H2O liquid. This is going to give me hydronium plus monohydrogen phosphate. This is what I did in my step 2. But why couldn't I have done the other collision? And so this is step 2 with Ka, but if we do step 2 with Kb, you know, because it's amphoteric, you got to worry about it acting as a base. We end up with this. So yeah, let's take a look at what we end up with. H2PO4 minus will be a proton acceptor, liquid, and so this will generate H3PO4 plus hydroxide. When we look at step 2b, step 2b is exactly the same as step 1, except it's in terms of pOH, whereas step 1 is in terms of pH. So it's just a seesaw, pH and pOH, it doesn't matter which one we use, you know? And so here, this is redundant. Redundant because it describes the equilibrium between H2PO4 minus and H3PO4 just as step 1 did. So the numbers will come out the same. And so this is the same as step 1. Right? Same as step 1, so we wouldn't bother. And so this is why the rule works. When we're looking for acids, we just look at the Kas, ignore the Kbs, because doing the Kbs would be redundant. When we're looking at bases, we ignore all the Kas because the Kas would be redundant. We just look at the Kbs, right? Uh-huh.
So we know that we're looking for Ka because we're given a strong acid. I mean,
Well,
because we're given an acid.
Yeah, because we're given an acid. But what if we're given an amphoteric? You know, and how are we given an amphoteric? Well, you know, if we're given an amphoteric, then what do we do? Because it could go either way. And so let's do an amphoteric. We'll do an amphoteric like H2PO4 minus. See, here there's no phosphoric acid. And so we're given H2PO4 minus. We have an amphoteric. What do we do? And so an example of this is, let's say we're given 0.100 molar sodium dihydrogen phosphate. So do we treat that as an acid and just look for the Kas? Or do we treat it as a base and just look for the Kbs? How should we do it? We do it as the base? Because what was bigger, the Ka or the Kb? The Ka was bigger. So maybe we should just treat it as an acid and just do the K.
It's a conjugate.
So Ka or Kb?
Should be seen on J.
We have to do both. We need to do both Ka and Kb. The reason we have to do both is this. Which one was bigger? Let's start off with the bigger one. Ka or Kb? We calculated Ka and Kb for this one earlier. Ka is greater, so let's do Ka. So if we do Ka, we got H2PO4 minus plus H2O liquid. This is Ka, so it's an acid. We donate a proton, so we'll get HPO4 2 minus plus hydronium. Right? This is our Ka. But we think, do we really have to do Kb? Do we have to do Kb? Well, let's take a look at Kb. Kb is going to look like this. H2PO4 minus plus H2O liquid. This is going to give us H3PO4 plus OH minus, or Kb. And so is that redundant? Are we solving a redundant equilibria? Did we already solve this equilibria? No, this is a unique equilibria. In fact, this is not redundant here. So we have to do both because we haven't described the equilibrium between H3PO4 and do you see the equilibrium between H3PO4 and H2PO4 minus in terms of pH? No, this is not redundant. And so we must do both. All right, so let's do it. And so how do we do it? We try to do it stepwise, right? We start off with the biggest K and then go smaller. And so starting off with the biggest K, that's going to be Ka, right? And so what we'll do is here, initial H2PO4 minus will be 0.100 molar. This is salt. Water, we'll assume nothing's happened yet. And so the change is going to be minus X molar, plus X molar, plus X molar. And so at equilibrium, we're going to have 0.100 minus X molar, X molar, and X molar. Ka is equal to the HPO4 2 minus times the hydronium divided by the H2 PO4 minus. And so this is going to give us x squared over 0.100 minus x. And we'll use a simplifying assumption, so we'll just get x squared over 0.100. And x is equal to,
I forgot. What was the Ka value for this?
That's just 3 times 3.
Is somebody having the answer?
0.0250.
Seems a little bit big, 25%.
It's not that strong of an acid, I think. I think it should be smaller.
Yes, that's 7.9 times 10 to the 5.
7.9 times 10 to the negative 5. Give me one more digit. 7.9 what? 3? Is that rounded or not? Okay. Okay, 7.93 times 10 to the minus 5. Okay, that sounds a little bit better because it's a pretty weak acid. And so this is going to be 0.100, but we can always check it. 4 zeros and the 793. So this is going to give us 0.0999. That'd be 2, 0, 7 molar. It's going to be 7.93 times 10 to the minus 5. 7.93 times 10 to the minus 5. Okay? All right, so what we're going to do is we're going to bring this down to step 2. And so this amount is going down to step 2. And what else? This is going to go to step, no, this doesn't go to step 2, does it? Only one thing goes to step 2. Is that right? Yeah, it looks like it. And so for step 2, let's take a look at what we have here.
Now we're working on KB.
I'm sorry?
Now we're working on KB.
Yeah, now we're going to work on KB. We just finished KA, let's do KB, right? Because both collisions happen for the same amphoteric species, right? And both yield unique species in solution here. And so let's try this. It's going to be 0.09999207. Water, leave out. Phosphoric acid, 0, and hydroxide, 0. Correct? Assume no collisions have happened yet. And so the change here is going to be minus x molar, plus x molar, plus x molar. Yeah. So we'll get 0.09999207 minus x, and then x
X molar, and then X molar. Kb is going to equal the phosphoric acid, H3PO4, times the hydroxide, divided by the H2PO4 minus. This is going to give us x squared over 0.09999207 minus x. And then we'll use the simplifying assumption. It's going to give us x squared over 0.09999207. And then solve for x. Somebody have it?
Yeah, 3.75 times 10 to the negative 7.
We'll just carry one extra digit. 3.75 times 10 to the negative 7?
Yeah.
Thanks. All right, so let's calculate the equilibrium concentrations. Did we double check this one? Sorry. Probably should double check it before moving on, otherwise we'd have to redo the calculation again. So I forgot to do that. Can somebody double check this one just to make sure it's okay? It's good? So that checks out, so we're okay. Go ahead and calculate this. So this is going to be minus 0.60. 1, 2, 3, 4, 5, 6, 3, 7, 5. So this is going to be 5, 2, 3, 9, 2, 9, 9, 9, 0, 0. All right, did the H2PO4 minus concentration change much? No, it didn't really change much at all, did it? That's good, because if it changed significantly, what would happen to step 1? It'd perturb it. It didn't perturb it, so we're good. And then the H3PO4 concentration is 3.75 times 10 to the minus 7 molar. And the hydroxide concentration is 3.75 times 10 to the minus 7 molar. All right, what's next? Huh. What's next? This is a little bit tricky. What's next? You know, we generated HPO42 minus. You know what HPO42 minus is? Oops, 10 to the negative 12. Is it 10 to the negative 12?
Yeah.
Sorry. I screwed up this calculation. This is going to be well, we would have caught it and double check, but 12 would be 11 zeros, right?
Yeah.
And so basically it didn't change. Right? And so this is going to be 3.75 times 10 to the negative 12, 3.75 times 10 to the negative 12. Hmm? It was this negative 7?
Yeah.
Okay. Just change it back. 7. But double check to catch it. Let's double check this and just see. You double check that and either way, it just doesn't change it much.
Yeah.
It comes out okay?
Yeah.
So this comes out okay. So what do we want to do next? What should our next step be? This is step 1, step 2. So this was 1.
Should we do the next hydroxide?
All right, what would the next hydroxide ion contributor be? Monohydrogen phosphate? You're right. Monohydrogen phosphate would do it. Hmm? What's that? It's also amphoteric. Monohydrogen phosphate's amphoteric. So we have a Ka and a Kb. If we do Kb for monohydrogen phosphate, let's see that. Let's write it over here. If we do Kb for monohydrogen phosphate, that's a proton acceptor. So we end up with H2PO4 minus and hydroxide. And look at that equilibrium. Did we already do that? Yeah, so we wouldn't do that here because we've already done it. So what would the next step be? Ka for HPO4, 2 minus? Actually, you're right. If we do Ka for HPO4, 2 minus, plus water, H2 liquid, this donate, so this is going to form phosphate and hydronium. Is that going to be a bigger contributor than water? Well, it depends. What is the Ka for HPO4 2 minus? Let's take a look at that here. Let's see what the Ka is. So, HPO4 2 minus is 4.2 times 10 to the negative 13, which means it's going to be a bigger contributor than water. So we should do that because that's going to contribute some more hydronium to this, right? Going to contribute more hydronium. Very much more? Well, let's think about that because the Ka for this was 6.3 times 10 to the negative 8. And so we're going from 6.3 times 10 to the negative 8 to 4.2 times 10 to the negative 13. Are we going to get much more hydronium from that? No. We wouldn't expect much more additional hydronium. Over here, would we get much more hydroxide? Well, we're looking at Kw. The most, well, what other hydroxide contributors are there? Water. And so this is 10 to the minus 7. It looks like we would get some more hydroxide from here. Now, if we're doing inventory, then we want to do everything, right? But if we're doing pH, then, yeah, we just worry about the contributors of that. But
The problem is this. I don't know if you see this right off, but do you see that the even though these are not tied together, hydronium and hydroxide are tied together by Kw. So if one goes up, the other has to go down, right? And the hydronium and the hydroxide have to multiply out to 1.0 times 10 to the minus 14. And so take a look at this. This is 10 to the minus 5, this is 10 to the minus 7. This is going to multiply out to about 10 to the minus 12. Maybe 10 to the minus 11. See, what we did was we solved these independent of one another, but these two equilibria are actually tied together. How are these two equilibria tied together? By Kw. So we could see how much more additional hydronium there's going to be, but let's focus on pH, and if we can stop, we'll come back to this if we need inventory. But if we can solve this, and so let's take a look at Kw now. We do Kw, and we'll do this as step 3, although, you know, 2b, we might have a step 2b. And so step 3 will be H2O liquid plus H2O liquid. H2O liquid plus H2O liquid, this is going to give us hydronium plus hydroxide. What's my initial hydronium I'm going to have in here? 7.93 times 10 to the minus 5 molar. My initial hydroxide, 3.75 times 10 to the minus 7 molar. What direction is the change going to be in? Is it going to go right or left, or which way is it going to go? You know, for me, I would use a trick here. I'd use a trick to make the math a little bit easier. You know what the trick would be? You don't have to. We can figure out what Q is. It turns out Q is going to be less than K. It's got to shift right. So this is going to be plus X molar plus X molar. And so at equilibrium, I'm going to get 7.93 times 10 to the minus 5 plus X. 3.75 times 10 to the minus 7 plus X. If you calculate Q. Does someone want to calculate Q to see what Q comes out to? Just multiply these two together and see, is it 1.0 times 10 to the negative 14 or less than or greater than? It's less than, so it shifts right. But you would have to do a Q calculation to predict the direction of the shift, right? Well, I never do Q calculations. You know why? I never do Q calculations because instead of doing this, I just reset it. You know, if I reset this to the left, which one is the limiting reagent? This is the limiting reagent, right? And so this one would go to 0. And then I lose, it's a 1-to-1 mole ratio. And so this one would be, I'm going to get in decimal form. So 4 zeros, 793. And this is going to be minus 5 zeros, 1, 2, 3, 4, 5, 6 zeros, and a 3, 7, 5. And so this is going to give me 5, 2, 12, 9, 8, 7, 0, 0, 0, 0, 0. Okay, and then the change would be plus X. And so at equilibrium I'd have 0.000078925 plus X molar and X molar. So does that really make it simpler? Let's see. So this is KW. Well, we'll do it. The KW without reset. KW without reset is going to be this binomial times this binomial.
KW with reset is going to be only one binomial. Uh-huh.
It's gonna be larger than K.
Oh, is it larger?
Yeah, because it's 10 to the power of negative 11.
Oh, that's right. It's larger. So this was wrong. This should be minus x. Sorry. And so this is going to be minus x minus x. Okay. I'm not very well practiced with cube calculations because I never do them. Actually, I don't bother. I don't bother because I just automatically reset this. I just reset this and then just use the SA. Could I use the SA here? I like using, you can tell I like using the simplifying assumption, right? Could I use the simplifying assumption in this case? No, I'd have to use the quadratic equation. I hate the quadratic equation. And so I'm going to go here and try to not use the quadratic equation, right? I'm going to use the SA and just say this is going to be quadruple 078925 times x, and then solve for x. Well, that's a lot easier, I think. And what does x come out to here? Even if I have to use the quadratic equation, I can get it much more rapidly in quadratic form from a reset than I could from a not reset condition, because multiplying binomials is another thing I dislike. So some people ask me why reset. Well, this is one of the reasons why I like to reset. This is a good example. And so x comes out to, well, this is equal to 1.0 times 10 to the negative 14. And so x is equal to, oh shoot, we're out of time. 1.26, oh, we'll just go 1.26 times 10 to the negative 10. And so when we look at the initial is 10 to the minus 5. And so 10 to the minus 10 divided by 10 to the minus 5 gives me 10 to the minus 5, right? Times 10 squared is 10 to the minus 3. This is 10 to the minus 3% change, so the simplifying assumption was no problem here. And so it didn't change here much. It's just going to be about the same thing. But it did change significantly here. It's going to be now 1.26 times 10 to the minus 10. Smaller. Now look at these concentrations. Did the hydronium concentration change much? How about the hydroxide concentration? Compare the hydroxide concentration to what we had earlier. Did this step perturb either step 1 or step 2? Well, what was the hydroxide concentration we had earlier? 3.75 times 10 to the minus 7. The new hydroxide concentration is 1.26 times 10 to the minus 10. Did it perturb it? Yes. We went from 10 to the minus 7 to 10 to the minus 10. That's a 10 to the third. That's 3 orders of magnitude change. That's a 1,000-fold change in hydroxide concentration. Now it's 1,000 times more dilute. Is that a significant change? Yeah, that's orders of magnitude. Our K calculation is going to be 3 orders of magnitude off now. It's not going to double check, which means that this step screwed up that step, which means that this is a simultaneous. But it's not a simultaneous with 2 equilibria. This is a simultaneous with 3 or 4 equilibria, which is a horrendous problem, right? And so we'll talk about this next time since we're out of time.